Yes, thanks for the nice introduction. Welcome to my talk, Securing the Darknet, or what is this nice combination YU63BGN and so on. I apologize in advance for this clickbaity title, but maybe I could attract some more interest out of that. You already introduced me, so my name is Jens Kubizil. By day, I am an IT security person and also work in the field of data protection. So you may have heard that the General Data Protection Regulation is there, and I help companies to be compliant with this GDPR. And as you already said, I'm a founding member of the Zwiebelfreunde e.V., which is a member of the Tor Serversnet community, and also Tor Serversnet itself was founded by some people of Zwiebelfreunde. And we help relay operators throughout the world to run relays. We support them with some advice in several regards, so in technical advice, jurisdictional advice, etc., etc., etc. And you also said I'm like a long-term contributor to Tor, so I was aware of Tor around, I think, 2004 or so. I met Roger Dingeldine, and since then I do several things in Tor. Yeah. And if you want to contact me, you have several possibilities. So there's this social network thing like Twitter. I have a handle at QBI, a GNU social handle, which is also QBI. I have a Ricochet address, which is a certain kind of protocol which runs over Tor onion services with that address, and you can also write me a mail. So that's some possibilities to contact me. Of course, you can also reach out to me and talk to me directly. The term Darknet, as you said, is quite common. Several people use the term Darknet, and I think everyone in this room has heard about this crazy word. And if you look at the media, what they're trying to sell you is that the Darknet is a place where you can buy drugs, like this one, for instance. Or you can also buy weapons there, like this toilet brush here. In Germany, it was considered a weapon some time ago. So this is the usual thing where the media dubs the word Darknet. But if you look at the origins of the word, you see that the term Darknet or dark web has some other roots. So several years ago, the idea was that you have search engines and they index the web, crawl the web, etc. And some part of the web can't be indexed, can't be crawled by search engines. And so this part of the web stays in the darkness. So search engines can't find this part, and that's why this part was called the Darknet or the dark web. And right now, the meaning is more like the bad thing in the web or something like that. So at least from my German perspective, that's how I see the media is treating this word. But if you look at this definition, one of the first things which come to mind, which are like a darknet, are intranets. So intranets are usually kind of networks where companies or organizations don't want to be indexed, their context on the public web, because you find some personal data in there, some company secrets and so on. And this is one possible example of intranet. And also quite popular darknet is Facebook, because also the Facebook content is mostly not indexed by search engines. So you see, this is quite a blurry term, but when media is talking about the darknet, they usually refer to Tor onion services, or as they were called, Tor hidden services. So that's usually the thing which they are talking about, and that's also the thing which I want to talk about a little bit more in the next few minutes. And also when you listen to some media production or read some newspaper, you often see pictures of icebergs. So there is some iceberg, and the media say, well, the normal, the clear web is the part which you can see of the iceberg, and below the sea there is the dark web. You can't see it, and it's it's like 90% of the web is somewhere hidden in the darknet, and and they try to scare people away. But when you look at the Tor onion services, then you have the possibility to also measure parts of the Tor network. So 2 years ago, I held a talk here with the title Measuring the Tor Network, and I showed several ideas and several means how the Tor itself measures the network and also how other projects measure the network. And if you look at those measurements, the first thing you see is that the several Tor relays, they advise their bandwidth. They say, well, I'm able to push like a gigabit per second of traffic or 100 megabit or some other amount of traffic. And they write this in their descriptor, upload it, and then you can add all of those numbers. And when you add all of those numbers, currently this is around 200 gigabit per second traffic, which the Tor network is capable of processing. So that's at the moment at least the maximum which is possible. And then you can go to a large company like Cloudflare or Akamai, which does some CDN for things or other things, and ask them, well, assume I have a network which has 200 gigabit per second of possible traffic, and this is the 90% of the web. And if you tell it to them, they will burst out laughing, and after some hours, when they will become quiet again, they say, well, 200 gigabit per second, that's basically nothing. They process way more data. So from that perspective, it's basically bullshit. But if you look a little bit deeper into the numbers, then you see that the Tor network itself currently only processes around 100 gigabit per second of traffic. So that's the real number which the Tor, which goes through the servers is 100 gigabit per second, but this is also not a good estimation. And so several people from the Tor Metrics project tried to measure how much of this 100 gigabit is actually onion service traffic. And it turned out that the onion service traffic is currently less than 1 gigabit per second. And this amounts to around about 3% of the Tor network traffic. You have to calculate a little bit the hubs. So the traffic goes over several hubs and so on. And so that's why the number goes at around 3%. So it's onion service traffic is around 1 gigabit per second. Usually it's lower. And when you look at some onion sites, you find one onion site specifically. And this onion site is run by Facebook. So Facebook has one presence in the Tor world. They has a Darknet page. And Facebook claimed some years ago that they had around 1 million users. And I would expect that many users, or a large amount of this traffic, of this 3% is actually Facebook traffic. So I guess the number is way smaller. So in general, I would say this iceberg picture is bullshit, and you should basically forget this, because this is, at least from a Tor perspective, a total myth. And another thing which you often hear, especially in media, is that the Darknet is a totally anonymous place, and criminals can't be detected there, so it attracts lots of criminals, and people do all sorts of bad stuff. So and then you try to enter some onion URLs in your browser, surf the dark web, so to say, and then you encounter something like this. So this is one example from Germany, where it says the platform and the criminal content have been seized by the Federal Criminal Police Office on behalf of the Attorney General's office in Frankfurt am Main. So in this case, the German police was actually investigating into some crime, some criminal site, and they seized the contents. And you will also find some of those things which are done by the FBI or some other law enforcement agencies. So actually, law enforcement agencies are not blind when it comes to the Tor onion services. They can do their investigation, and they do it. And there's another example from Germany. I couldn't find the English version of this news. So you see here the a German headline, and this is about a case in Germany where some kid ran a truck shop from its parents' home, so from his children's room. Basically, he stored a huge amount of drugs and sent drugs from his home to the customers. And what he basically did, he had first a site called shinyflakes.to. Then later he went to the Tor hidden services and had some presence there. And he took orders from his customers, made some nice little package, went to the post office and sent the package to the customer. And in some cases, the address of the customer was not correct and the package was sent back. But there was no address on the packet, so it landed in the post office, and they had no idea how to contact the person, and so they opened the packet and saw, oh, drugs inside. And so they called the police. So this happened one time, the next time, another time, and so on and so on. And then the police came to the idea, well, maybe this guy uses this exact post office to send his truck to the world. And then they surveilled the place a little bit and then found the guy and raided his home, and so found a huge pile of different kinds of drugs. They took his computer, and when they later analyzed his computer, they found a small file on his computer with a name similar to orders.xls. And well, they opened the file, and orders.xls contained the orders, as you might imagine. So it was a list with each name of the customer, the address of the customer, and how many drugs the people bought. So the police had like a complete order history of all the people there. And right now, police is going from line to line in this file and goes to the customer of the Shiny Flakes site and also try to get them. So it's not really, as you can see, an anonymous place. The FBI took it a little bit further. They took down also some Tor Onion site. And so, well, at first they didn't really took it down. They kept running it and sent a small, let's say a bad packet, so it was an exploit for the Firefox, to everyone who visited the site. And this exploit sent back the real IP address of the person who was visiting this Onion site. So the FBI was able to reveal the real IP address of people who are visiting the sites, up to a point where Firefox detected this flaw and closed the flaw. So also this was done, and there are some rumors that also law enforcement agencies do this and try to buy 0 days and try to get onto other people's computers nowadays. And several days ago, there was another line that the Australian police ran a site which contained images of child abuse, also to detect who visits the sites, and they kept running it for 11 months. And so my assumption is that if you go to the Darknet, to the Tor Onion sites, and really go to this, like let's say the shady area there, like the truck places, there's a high probability that those sites are run by some law enforcement agency or some other strange people. So it's not a totally anonymous place and where nobody can be found. Actually, police is investing quite heavily in this area and try to detect where the people come from. So, and I already said some words about Tor. I would expect that every one of you has heard about Tor. So it's a software to communicate securely. It offers anonymity on one hand side and also censorship resistance. And I hope every one of you has heard about the principle that when you run a Tor client, then you download a list of all existing Tor relays in the world, and your Tor client then selects 3 relays and builds a multiple encrypted connection over those 3 relays to the endpoint. So that's in very short words how Tor works. And Tor itself consists of several sub-projects. So there is the Tor metrics project, which I was talking about earlier before. There is, for instance, the Tails project, which is a complete live CD, which transfers all traffic over Tor. You have the Tor daemon, the little t Tor, and also the Tor browser and several other projects. So Tor at the moment consists of more than 40 sub-projects. And also Tor is a community of developers, researchers, server operators, etc. So you have lots of researchers which try to attack the software or the protocol, people who are trying to improve the software, and also other people who run the thing. And the thing which you should have seen before maybe is the Tor browser. I said it before, this Mozilla Firefox, basically, and Tor patches this version of Firefox to just tries to improve the privacy preserving mechanisms there, and also there's included the Tor client, Tor button, etc. And right now there's quite a good cooperation between Mozilla and Tor. So Mozilla has a so-called Tor uplift project, so they take some of the patches from Tor and build it or include it into the normal Mozilla Firefox, so that also the privacy features of the normal Firefox are improved. So that's quite a nice thing. So that's usually the thing which you see when you go to torproject.org, click on download and install, then you see the Tor browser. That's the usual thing. And one feature I was talking about in general terms are these Tor onion services. And this back in 2004, Roger Dingeldine, one of the founders of Tor, had the idea to offer also the senders of information anonymity. So back then, only the receiver of information, so people who are browsing the web, have some kind of anonymity, and he wanted that also other people can have a web server and run a site there, and nobody should be able to detect where the server lives, what its IP address is, etc., etc. And that's why in 2004, those so-called hidden services were developed. And you might ask yourself, how do they work? How is the general principle? And I have here 6 slides which show the design of Tor hidden services. So on the right-hand side, you see here Bob, and Bob is the person who wants to offer some websites, wants to have offer a hidden service, and so first he sets up his web server and sets maybe up a blog or a static site or whatever, and configures its Tor client. And then the Tor client uses some introduction points inside the Tor network. So this IP 1, 2, and 3 are normal relays inside the Tor networks, and Bob picks, in this case, 3 of them and builds a circuit to them. So he builds just a normal Tor circuit to them over 3 other hops. And when this is finished, he will then build a descriptor, a so-called descriptor, which contains some information about the introduction points, his public key, and some other information, and uploads this to this DB over there. So that the term is HS directory, hidden service directory, and this will play a role in the next slides. So, and then Bob is finished. Bob has this connection to this introduction points, uploaded his descriptor, and then waits what happens. And at some point, Alice learns about this onion address, xyz.onion in this case, and what Alice then does is she connects to this hidden service directory, to this database server over there, downloads the descriptor, and makes also a Tor connection to another point inside the Tor network, which is called RP, rendezvous point. And when she does this, she keeps this connection to the rendezvous point and makes another connection to one of those 3 introduction points Bob chose before, and sends some information over there. So she sends some information about the rendezvous point, sends some more or less random value, the cookie, and some other information to the introduction point, and the introduction point then delivers this information to Bob. So, and Bob now has all this information and also makes itself a connection to the rendezvous point and sends the information about, with this random value, the cookie and other things, back to the rendezvous point, and the rendezvous point then connects both of those circuits. So in the end, Alice has a 3-hop connection to the rendezvous point, and Bob has a 3-hop connection to the rendezvous point. So the rendezvous point has no idea who is connecting to him. So he just transfers the connection and has no other idea. And so this is then the established hidden service connection, and both can communicate in a secure way. Especially neither the rendezvous point nor Alice can learn about the real IP address of Bob, at least in theory. In practice, there are a number of attacks which can detect the geographical location where such a hidden service lives, and depending on how good you are at setting up web servers and so on, it might be easier to detect this. So many people, or one of the usual things which people, one of the usual faults which people do, is they set up a web server, run some service over there, and if you think of the Apache web server, for instance, there is this page called server-status, and this can be reached over your local interface, but the Tor onion services also talks about over the local host, over the local interface, 127.0.0.1. And so what you can try is, when you have such a hidden service, enter the URL /server/server-status, and in some cases you see the Apache status page and see real IP addresses, and then you're able to detect where this thing is. And also there are some more esoteric attacks which deal more or less with operational security, and but I won't go into detail about this. You find some documentation in the web. More interesting is the whole idea of the descriptor. So as I said before, in step 2, you see here a small image. Bob sends the descriptor to the hidden service directory, to this database which was over there. But you might ask yourself, what is the descriptor? What's contained in this descriptor? And when you look at the documentation, you find that this descriptor contains the onion key. And the onion key is the first 80 bits of the SHA-1 hash of the 1024-bit RSA key. And if you look at the sentence, are there any words inside which concern you? Raise your hand if you have any concerns with any of the words inside this item. You? Has someone another? Yeah, you order? Yeah. Yeah, I will repeat it, yeah. So, but what I heard was really correct. So, in my opinion, every word in the sentence sounds wrong to me. You said it, 80 bits of the is a problem. SHA-1 is a problem. RSA 1024-bit is also a problem. So, as I said before, this hidden service design is from 2004, and it's not up to date. So it has several problems, and it needs to be updated. And Tor did go to great lengths to update its cryptography. So several steps of the protocol were updated, and basically the hidden service design was the last step which needed to be updated and which is now updated. Another issue is the descriptor itself. So the descriptor, which is then uploaded, is a hash of the onion key above, and into the hash goes the time and some other data which are well known. There's some 0 which goes in there, some empty value and so on. But all of the values which go inside in the calculation of the descriptor is well known. And So you might want to decide to calculate the descriptor of a specific hidden service site. Let's say from WikiLeaks. You want to calculate the hidden service descriptor from WikiLeaks, which is from the next year. So you have the information about the time. The onion key itself is public. You find this is on the web. And the other data you can guess for itself. So it's quite easy. It's some hashing is done. And then you know the hidden service descriptor of the WikiLeaks site in the next year. So and when you know this, then you can create or you can create a Tor relay with with an identical key. So what Tor does here when it calculates the descriptor, it looks for a Tor relay which has a quite similar beginning to this descriptor here. So it's basically a hash ring. And what you can do now, you can use some kind of software and calculate, or can say to the software, please, dear software, the hidden service descriptor of WikiLeaks starts with 1, 2, 3, 4. Please create me a server key, which also starts with 1, 2, 3, 4. And when you've done, you inject this into your Tor relay, start your relay, and then wait. And at some point in a year, at this chosen date, the WikiLeaks hidden service will then connect to your hidden service directory, uploads its descriptor, and when it's then uploaded, Alice, as in the example before, will come and download the descriptor. So what you can do then is measure how popular one specific hidden service is. So you can do some measurements how popular the WikiLeaks site is, for instance, or any other hidden service site. So this is called a hidden service directory camping attack, and this is really done in the network. So it is not a theoretical example. Right now there are companies outside which do exactly this attack. They calculate the hidden service keys and then start Tor relays with exact this key and wait until other hidden services upload their key to them. And inside Tor, there are people which try to detect this attack and exclude those nodes out of the network. And this is really an arms race, and also for Tor, quite a problem at the moment. So, and that's why they decided we have to improve the whole system, and I will show some improvements in the next slides. As I said before, one problem was quite old cryptography. Tor decided to use some better cryptography, so they chose elliptic curve cryptography. They have the ED25519 curve, and they use as a hash algorithm the Ketchak algorithm, the new SHA-3 algorithm. This has, of course, an improvement in security, but what you can see here is that the old onion addresses were 16 characters long. So you see here the onion address of the New York Times, which starts with NY Times, 3X, and so on. And right now, the new onion addresses are 52 characters long. So this does YU63BJN and so on. And you will have quite a hard time to enter this onion address. I did this for you. And if you enter this YU363BJN, you will come to this nice site. But I created this onion service, so it's not an official DeepSec service. So I created this on my computer. So if I shut it down, also the website, or you won't be able to go to this website anymore. So it's just for the presentation here. So the onion addresses are now a little bit longer, but the usage of better cryptography is really a big step forward. As I said before, the current function which calculates the descriptor is quite predictable. You can, if you know the input variables, and so you can you have several attacks. So what the new design does is they include into the calculation a shared random value. So what they did, or they discussed it quite a lot, the top developers, because the project needs a random value which is known to several parties and must be computed at each and all of these directory authorities. And this was not so easy, and they came up with this commit and reveal protocol. And you find a quite detailed overview in proposal 250. So Tor, when you want to improve Tor, you have to write a RFC-like proposal, and this thing has the number 250. And this usually such proposal will discussed among developers, researchers, and so on. And when everyone thinks it's a fine idea or a good idea, then it will get implemented. And proposal 250 is implemented right now into the code. And the idea is that the directory authorities, currently there are 9 of them, they generally make a consensus voting. What they do is they vote on each and every relay. If they think it's a good relay, a bad relay, it's fast or slow, and so on and so on, they do it on a daily or hourly basis. And right now, the shared randomness is a new thing which is also included in the protocol. At the beginning of each day, each directory authority just calculates a random value. And then it starts the so-called commitment phase. So they build more or less a hash value of this random value. There are some other information also added, but just for simplification, assume that is a hash value, and this will go to a commitment phase. So it will send to all other directory authorities, and they record this value and just wait. They wait for 12 hours. Around in the middle of the day at 12 UTC, there starts the reveal phase. So where each of those directory authorities says, well, my random value was this and that, and the other directory authorities can compare or can calculate the hash value and can see if it's really the same value which they received before. And then after another 12 hours, they basically hash all those 9 values together, and this is the new shared randomness value. As I said, it's a simplification which I said here. If you want to know the details, please look into the proposal 250. This means the shared random value is then known to each and every directory authority, and it changes each day. And this also goes into the formula to calculate the hidden source descriptor. So an attacker only has like 24 hours time to pre-calculate some keys and to start its relay in the network, to wait until the network gets some trust in the network. And this is usually this amount of time is too slow to successfully start this attack. So right now, the assumption is that between 30 and 40 days it takes to calculate the key. Then you need also between 20 to 40 days to get your relay in the exact position. So it takes quite some time. And now with new design, you just have 1 day, so 24 hours, and then there's a new random value which you can't predict. So this is really an improvement and stops this kind of attack. But there's more. So currently the onion service uploads the descriptor to the hidden service directory, as I said before. And the hidden service, so the onion key is part of this hidden service descriptor. And this hidden service directory learns about the onion key, about the address of the hidden service. So this is not a problem in the case of Facebook or New York Times and so on, which want to have like a public-facing service. But if you want to have a real hidden service between you and a friend, maybe, it's not a good idea that some third party, which you don't know and have control of, also learns about the address of your hidden service. And also, currently with the current design, there is not much what you can do about this. The Tor project also here tries to learn about relays which try to harvest onion addresses and throw them out of the network. But also this is an arms race, and it draws quite lots of efforts to detect those relays. With the new cryptographic things which are inside, it's possible to have a subkey. And right now, the descriptor is then signed with a subkey, and you can't conclude from the subkey to the main key. And that's why it's not possible anymore that the hidden service directory learns about the address. So also this kind of attack will go away with the new design. And another nice thing which comes with the new design are so-called single onion services. So as I said before, when Alice connects to the hidden service of Bob, Alice has a 3-hop connection, Bob has a 3-hop connection, and this will take some time. And I talked about the hidden service of Facebook, of the New York Times. They usually don't want this, want to hide their location. Usually it's crystal clear where their servers live. They want better performance. And so here for them it's possible that they only use a single hop connection, just one hop, and then connect to the rendezvous point, and Alice on her side goes over the normal Tor connection, so you only have like 4 hops in between, and this gives quite better performance for such services. So all those things which I said before are now rolled out in the current Tor code. If you run the Tor, or if you download the Tor browser and install it, you can use all these features. But there are, of course, some bugs inside, and Tor is trying to improve the code. And also there are some other to-dos, some improvements. So you might be able to remember the 16 characters of your onion services. Maybe 1 or 2 people in the room are able to remember the 16 characters of the New York Times onion service. Or maybe I should ask you, can someone give me the address of the New York Times address? So it was on some slide. Here it is. Here it was NY Times 3XBF GRA GH, but it's quite hard to remember this address. But yeah, as I said, some people are able to remember the 16 characters, but ask yourself, how good are you at remembering 52 characters? It's next to impossible, I would say. And so what Tor is currently thinking about, how they can have a good naming scheme, which is secure and also memorizable. And yeah, currently there's nothing set here in this area. So if you have a good idea about naming schemes, then I would recommend talk to the Tor developers or talk to me, and we can discuss what you can do for Tor, basically. A very large problem one problem at the moment are so-called guard discovery attacks. So when you create a Tor connection, then your Tor client goes to the first node, then the second node, and then the exit node, and then leaves the Tor network. And the first node is usually called guard node because it will stay for some days or weeks. It will stay the same node with your client. And in connection with hidden services, there are some attacks possible to reveal guard nodes and to also reveal the identity of hidden services. And also this kind of attacks are run inside the networks. And here there are 2 proposals, the proposal 247 and 271, which will improve it a little bit. So in the future, you will not only have one guard node, but several guard nodes, and the churn rate of those nodes is different. So some will go away after several days, one will stay for weeks and months, and also this will give more security in the future. But also this needs to be put in the code and takes some time. So currently you are also able to manage your Tor client over a so-called control protocol, over the Tor control port. So you can like open a telnet connection and send a command to your Tor client and make new settings or change the circuits and so on. And for the hidden service design, it's also quite open at the moment how the control protocol will work and what kind of things will build into this thing and not. And also here, if you have ideas how to implement this in the software, how to implement it in the protocol, it's a good idea to talk to Tor. And the same is with client authentication. Also, the Tor has developed some ideas how to do client authentication with the hidden service protocol. Also, this is a big to-do at the moment. So a large chunk of the new design is already done. It's rolled out in code and can be used. But you can see here there are quite a few things which need to be discussed, which need to be written in the code and they are developed. So it's not finished yet, but at least I wanted to introduce you some of the improvements. And thanks for listening. If you have any questions, please ask your question and consider running a relay and improve the overall performance of Tor. Thanks.
Question? Yes. Test. Yeah.
So, have you seen any like malicious relays, or to be a bit more precise, hidden service directory servers, which then refuse to serve the descriptor for a particular hidden service in order to temporarily make it unavailable?
So I haven't seen such attempts yet. So what we assume is that most of them just try to measure the popularity of a hidden service.
Any more questions on old style or next generation onion services? Oh.
You said you can, how should I say, make your hidden service faster, but you're not so good hidden anymore. So
could you place the mic on your?
Okay. You said you can make your hidden service quicker, faster.
Yeah.
But it's not hidden so good anymore.
Right.
Problem. Do I configure that in Tor RC? Where does the user configure that, or who configs it?
Yeah, you configure this in your Tor RC. There's an option in the Tor RC. Would have to look it up.
Okay.
If you look for a single hop onion service, then you will find this option.
Okay. Thanks.